students. Today we shall look into the intensity of the different spectral lines in the rotational spectrum, the non-rigid rotator, and the information that we can derive or understand from such a rotational spectrum or microwave spectrum. Now, this is a picture of the rotational spectrum of hydrogen chloride. In this, you can see that molecules have absorbed energy and they have given the radiation of frequencies in these particular wave numbers. And hence, these frequencies have been recorded in the spectrum. All these frequencies are equally spaced among themselves, and that spacing is equal to 2b. Here, the intensity of each of these spectral lines, it depends on two factors. They are the number of molecules present in each energy level, and that population is given by the Boltzmann's distribution. The second factor is the degeneracy of each energy level. Let us look into that. Now, assume that Nj is the number of molecules in the jth energy level, in the jth state. Hence, the population or the number of molecules in the jth state, Nj, is proportional to the population according to Boltzmann's distribution, that is e raised to minus Ej by kt, exponential of minus Ej by kt. It is also proportional to the degeneracy of each energy level. Each energy level is said to have 2j plus 1 folds of degeneracy. That is, 2j plus 1 number of states have the same energies. All of these energy levels are called degenerate energy levels. So, Nj is proportional to these two factors. 2j plus 1 is due to the degeneracy of the energy levels, and e raised to minus Ej by kt is due to the population distribution of the molecules according to Boltzmann's distribution. Now, substitute for Ej in terms of the rotational constant b. Hence, we will be able to write Nj is proportional to 2j plus 1 into e raised to minus hc b into j plus 1 divided by kt. Now, removing the proportionality constant, we can write Nj is equal to the constant a into 2j plus 1 e raised to minus p j into j plus 1. Here, p is just a random constant that is given here for ease of the calculation in the further steps. So here p is equal to bhc by kt. When the population Nj is plotted against J, we get a curve. The nature of curve is like this. Here from this curve we can understand that the population rises as the J value rises. It rises up to a maximum, and after that particular J, it decreases. The population decreases. So even if there are different J levels, J states, maximum population will be in a particular J state. The intensity will be maximum for the J value corresponding to the maximum Nj value. So where the population is maximum, those molecules or the molecules in that energy level interacting with the microwaves will be greater in number, and hence the intensity of that spectral line, that frequency, will be higher. Now, to find the particular value of J, we differentiate Nj with respect to J and equate it to 0. We do this because according to this curve, here we can see that curve, its slope is 0 at the peak. Hence, derivative will be 0 there. So, taking the expression for nj and finding the derivative, nj is equal to a into 2j plus 1 into e raised to minus p j into j plus 1, where p is equal to bhc by kt. Taking the derivative d by dj of nj, get here we have the product of two terms. Hence, the first term a into 2j plus 1 into derivative of second term, that is e raised to minus pj into j plus 1 into minus p into 2j plus 1, right? Then plus 2a times e raised to minus pj into j plus 1. So we took the derivative of the first term here and then wrote down the second term. Here we have the term 2j plus 1 because in the second term we write this term as j square plus j e raised to minus p j square plus j, and the derivative of that j square plus j will be 2j plus 1. Okay. Now at the peak of this curve, the derivative will be equal to 0. Hence we can write 0 is equal to 2 into 2j plus 1 e raised to minus p into j plus 1 into minus p into 2j plus 1. So we have 2j plus 1 twice here. Then the next term is plus 2a e raised to minus p j into j plus 1. Let us take the negative term to the left hand side. So we will be able to write a p into 2j plus 1 the whole square e raised to minus p j into j plus 1 is equal to 2a e raised to minus p j into j plus 1. We have similar terms, a e raised to minus p j into j plus 1 on either side. So cancelling it, we get p into 2j plus 1 whole square is equal to 2. That is 2j plus 1 is equal to square root of 2 by p, and we can write j is equal to square root of 1 by 2p minus half. Substituting for p in terms of the rotational constant, we had just taken this substitution for ease of the calculation. So substituting back, we get j equals root of kt by 2 bhc minus half. Now, the transition from this particular j level will have the maximum intensity. Now, the second factor that contributes to the intensity of the spectral line is the degeneracy of each energy level. So, an energy level is said to be degenerate if there exists two or more energy levels with the same energy. That is, the molecule may rotate in two different manners, but still both of those rotations may have the same energy. So they will be represented only by a single energy level, but in fact, in actual reality, they are two different energy levels of the same energies. So in these cases, we call it as degenerate energy levels. Now, the number of energy levels possible with the same energy is called its degeneracy. So if degeneracy is 2, we have 2 energy levels of the same energy. If degeneracy is 4, we have 4 energy levels having the same energies. Now, the energy of a rigid rotator is given as E is equal to L square by 2I, where L is the angular momentum and I is the moment of inertia. Hence, we can write angular momentum of the rigid rotator as L is equal to square root of 2EI. Now let us substitute for energy E. Then this expression becomes square root of 2I into energy is written as J into J plus 1 H cut square by 2I. So 2I cancels out and we get angular momentum is equal to square root of J into J plus 1 into H cut. So here we can see that angular momentum has the unit of H cut. This picture depicts, it shows the ways in which this molecule can rotate. If the angular momentum has value 0, it will rotate in the LX/LY plane in a perfect circle, as if it is moving on a disk. It will rotate in that manner. Now, when the angular momentum value changes, if it has integral values of 1, 2, 3, etc., it will start to wobble along the LZ axis. It will rotate along the cone with the central axis LZ. Okay, so depending upon the different energies, it will rotate along different cones seen here in the picture. Now for the first case, let J be equal to 1. Then angular momentum will be equal to root 2, that is 1.414. Angular momentum can have integral values ranging from this plus 1.414 to minus 1.414. That means it can have values 0, plus 1 and minus 1. This implies that angular momentum can have 3 orientations with respect to a reference direction. Now let this be the reference direction. Hence, the molecule can rotate with angular momentum 0 or angular momentum plus 1 or angular momentum minus 1. It cannot have the value plus 2 or minus 2 because L has the upper limit of 1.414. It has not become 2. So unless it becomes 2 or greater than 2, it will have only values minus 1, 0 and 1. The 3 ways in which the molecule can rotate with the same energy are shown here. So for L is equal to plus 1, the molecule can rotate along the cone that is facing upwards. For L is equal to 0, the molecule can rotate along this LX/LY plane along the surface of this disk. And if L is equal to minus 1, the molecule can rotate along the cone that is facing downwards. All these rotations will have the same energies and hence the energy levels for these rotations are said to be degenerate. Now if J is equal to 2, the angular momentum is equal to 2 into 2 plus 1. That is 2 into 3, that is 6. So square root of 6 is 2.449. L can have values ranging from plus 2 to minus 2. That is, L can have values plus 2, plus 1, 0, minus 1 and minus 2. That is, angular momentum can have 5 orientations with respect to the reference direction. If this is the reference direction, the angular momentum can have values along 0, plus 1, plus 2, minus 1 and minus 2. So that molecule will rotate along the surface of this vector. and that can be visualized here. So according to this picture, the molecule having angular momentum 0 will be rotating along this disk on this plane of the Lx and Ly directions. Now the molecules having angular momentum +1, they will rotate along this cone having amplitude h cut, and molecules having angular momentum +2 h cut will rotate along the cones of vector amplitude 2 h cut. Likewise, molecules having angular momentum -1 will rotate along the cone shown here, and molecules having angular momentum -2 h cut will rotate along this cone. Now for j equals 3, the angular momentum L is equal to square root of 3 into 3 plus 1, that is square root of 3 into 4, that is square root of 12. We get 3.464. The integral values of L will be plus 3, minus 3, plus 2, minus 2, plus 1, minus 1, and 0. That is, the angular momentum can have 7 orientations with respect to the reference direction. Again, if this is the reference direction, the possible values for angular momentum is shown here, and these are the possible directions of rotation that these molecules can have. So these molecules can rotate in 7 different ways, and all of these rotations have the same energies. That is why that energy level is said to be degenerate. Now, we have learned about rigid rotators till now, but in practice, in reality, all molecules are non-rigid rotators. That is, when the molecule rotates, its bond length changes. When higher energy is given to the molecules, its rotational energy increases. That is, it is raised to higher energy levels of higher J values. As its rotation increases, its bond length will increase. And if bond length R increases, the rotational constant B will decrease, since it is inversely proportional. Now this will lead to a separation between the lines, a decrease in the separation between the lines in rotational spectrum. That is, if B is decreasing, the spacing to B will also decrease. Now another factor is that when the bond is elastic, the molecule, in addition to rotation, will also have vibrational energy. It will also vibrate. Thus, the energy of the jth state can be written as eta j is equal to energy due to rotation plus energy due to vibration. That is, eta j is equal to B into j plus 1 minus d j square into j plus 1 square. Here, the centrifugal constant d is related to the rotational constant as 4b cube by wave number nu bar square, where wave number nu bar is equal to nu by c. In terms of force constant k and reduced mass mu, wave number is equal to 1 by 2 pi c into square root of k by mu. Here B is equal to h by 8 pi square I into C. Now substituting for the B and nu bar values, we get D is equal to h cube by 32 pi raised to 4 mu square r raised to 6 C K. Again, the selection rules here are the change in J, that is delta J is equal to plus or minus 1, same as of the rigid rotator. Thus, the energy difference between these energy levels, or the radiation for such a transition, the frequency of the transition from J to J plus 1, can be given as the delta eta j to j plus 1, that is the frequency of that radiation, in terms of wave number nu bar j, is calculated from eta j plus 1 minus eta j. Doing those calculations, we will get delta eta j to j plus 1 is equal to 2b into j plus 1 minus 4d j plus 1 whole cube. Here, d is the rotational constant, j is the rotational quantum number having integral values 0, 1, 2, 3, etc. and d is the centrifugal constant. By drawing the energy levels according to this equation, we see that for the non-rigid rotator, the energy levels are decreased. It is due to this term minus 4d j plus 1 whole cube. So these energy levels are decreased, they are lowered, and because of that, the spectral lines of the non-rigid rotator, they are shifted. That is, the 2b spacing is reduced. So, from the rotational spectra as seen here, we get a lot of data about the molecules. First one is that from the spectrum, we can directly measure the spacing between the spectral lines 2b. Now from that, we get the value of b, and if we know b, by using the relation b is equal to h divided by 8 pi square I c, we can calculate moment of inertia I. Now, if the reduced mass of that molecule is known, we can calculate the bond length R from the relation I is equal to mu R square. Now, the second factor that we can understand from the rotational spectra is the dipole moment of the molecule. By understanding it, we can learn about the nature of the molecular bonds. Now, the third factor we understand from this rotational spectrum is we can calculate the atomic masses using isotope substitution. If we have different isotopes, we can measure the isotopic mass using rotational spectroscopy. We have the relation, the primes are given for the readings of the isotope. That is, B prime by B is equal to I by I prime, that is equal to mu by mu prime. So, if we have the rotational spectra of the molecule, actual molecule, and the rotational spectra of the isotope substituted molecule, from the first spectrum we get B from the 2B spacing, and from the second spectra we get B prime from the 2B prime spacing. And if the reduced mass of the actual molecule mu is known, we can calculate mu prime, reduced mass of the isotope. So, knowing B, B prime and mu, mu prime can be calculated. That's all for today's session. Thank you.